Good day, everybody. Today I hope to make a quick video on how to find a potential for a conservative vector field. So first, a little preliminaries. I'll use the notation for a two-dimensional field P and Q of X and Y, or three-dimensional P, Q, and R. And then we have the result for a two-dimensional field. If P sub Y equals Q sub X, the vector field we know is conservative, at least on a simply connected domain. And similarly, on a simply connected domain, if the curl of F is 0, although sometimes we're just told the vector field is conservative, and then we are asked to find a potential. So how do we find a potential? The rigorous way, I suppose, is the way I see in all the textbooks and everywhere, and it's not really the way I go about it. I sort of exploit the fact that if F is the gradient of some potential little f, then this P is F sub X and Q is F sub Y. So I kind of want to anti-differentiate P with respect to X and anti-differentiate Q with respect to Y. Kind of an anti-partial derivative in a way, but and then we collect, sometimes we get repeated terms, we collect all the terms. I'll put that in quotes. I don't know if there's a rigorous process there, but we'll collect all the terms, repeated terms just once. So an example will certainly help. So here's a not too difficult vector field. If I check that it's conservative, P sub Y is 3, Q sub X is 3, so P sub Y is Q sub X. So this should be F sub X. So I want to anti-differentiate it with respect to X. And it's not too hard to do. We get X squared plus 3XY. Again, it's kind of an anti-partial derivative with respect to X, regardless. And then we anti-differentiate this with respect to Y, and we get this. And now we just collect all the terms, repeated terms just once. So I get X squared plus 3XY. This 3XY is already there, so I don't write it a second time. Minus Y, that's a new term. So this will be my potential. And you could add an arbitrary constant if needed. Usually we don't. And I might pay to take the gradient just to kind of see what goes on. So if I take the gradient, F sub X will be 2X plus 3Y, and F sub Y will be 3X minus 1. And notice this term with both an X and a Y, when you take the derivatives, it goes into both terms. And that's why when I anti-differentiated it, it was repeated. But when we form our F, any identical term, you just count once. Sometimes I'm asked, can we have two terms that aren't exactly the same? And so if I just modify that previous problem and make this a 2x instead of 3x, and if I were to do the same process, I won't exactly write it out, but if you anti-differentiate this with respect to x, anti-differentiate that with respect to y, then we get similar terms but with a different coefficient. And, well, the thing is, this f is not conservative. If you look at P sub y, it's 3, Q sub x is 2, so it's not conservative. So this is really a meaningless operation. And it's always recommended you check that it's conservative first, and usually it's required. But you can't have similar terms but with slightly different with different coefficients if the vector field is conservative. So if you check that, it won't happen. That you'll get near misses, so to speak. One more extremely complicated example. Just look at the whole thing here. So we've got all this. If you want to check that it's conservative, P sub y, take that derivative 8, or 16, I should say. 16x squared y cubed, P sub y here, negative 3 sine y, and then the y derivative here. And if you use the product rule, derivative of the first times the second plus the first derivative of the second, and the y derivative will bring me an x. And if you check the x derivative of this, the x cubed cancel, so that'll match. The x derivative here will match the x derivative here. Again, the product rule will end up matching, and then x derivative here is 0. So p sub y and q sub x will both be that, if you want to check. So to find a potential, all I'll do, again, this is kind of a complicated example, but integrate, anti-differentiate, I should say, my p with respect to x, and anti-differentiate the q with respect to y. So I'll get 4/3 x cubed times y to the 4th plus 3x cosine y, right? The cosine y is like a constant term. And when I integrate or anti-differentiate this with respect to x, it's like a constant times x, so you divide by that constant. Of course, now the y's are going to cancel. And antiderivative of 2 will be 2x. If I anti-differentiate this with respect to y, it'll be y to the 4th over 4, and that'll give me this. Anti-differentiate this with respect to y, I'll get negative cosine y times that. And you can kind of check that it's matching along the way. There's a little double check. But anti-differentiate this with respect to y, again, e to the xy divided by x, if you do the y antiderivative. And then y to the negative 2, the antiderivative will be negative 1 over y. So if I collect all the terms, repeated terms just get counted once. Most of these terms were repeated. These first 3 matched. But then there was a plus 2x and minus 1 over y. And could also add in plus a constant if you like. And I won't do it. But if you take the gradient, again, you'll see, when I take the x partial derivative, I'll get those terms. And when I take the y partial derivative, I'll get these terms. And that's why there was repeats. They're coupled, we sometimes say. And this gets generalized for a 3-dimensional field. If p is f sub x, q is f sub y, and r is f sub z, then I just do these 3 integrals, and repeated terms still just get counted once. So here's a medium example. I'm not going to test the curl, but it is the 0 vector. So if I anti-differentiate p dx and q dy and r dz, won't be too hard to do. We'll get 2xy cubed plus 2x squared z. This will be y cubed over 3 times the 6x, so it'll be 2xy cubed. This will be times z, and z cubed over 3, so we get that. So f, if I collect all the terms, is this plus this. That was already counted, so don't write it again. That was already counted, so don't write it again. But that's a new term. So collecting all the terms, I get this. And you can verify the gradient will work. One more really tough example. So if I have this f, kind of go overboard here, but there's my f. I started with the potential, and then I took the gradient, so I knew it was conservative, but I have full faith. The curl will be 0 vector. So I want to integrate p dx, there's p, q dy, r dz, and won't be too bad. Just a lot of terms. So 3x squared over 2 times yz, x squared over 2 times 2, x times the cosine. And then over here, if I integrate with respect to y, just insert the y. This will be y squared over 2 times 4. Integral of sine of yz dy will be negative cosine, and then divided by that constant z. And again, the 2 negatives and z cancels. It'll look like that term. And then if I integrate this dz, I'll get a z. Z squared over 2 will be 3z squared. integrate this with respect to z. You divide by that constant y, so negative cosine. So a lot of repeated terms. In fact, all three of these get listed, and then that was repeated. This is a new term. That was repeated. That was repeated. There's a new term, and this one's repeated. So if you collect all the terms, repeated terms just once, there you go. And for me, it's a little easier than doing the textbook method. Most examples you see, you might even be able to do in your head. Here's a simple radial vector field. Just do it in your head. Integrate the p, q, and r, dx, dy, dz. You have your potential. All right, so there's the video. Hope that helps you get your potentials without too much trouble. Thank you and have a good day.